Hi guys. So that video was about, previous video was about the formulas, and now we're gonna do a practice problem, how to think of problems using energy diagrams. So really the basic questions are gonna be what's in the system, where is energy stored in snapshot A, and how does that change in snapshot B? When I say snapshot, I mean like a moment in time, like an instant. The example that I have for you right now is, let's say a ball is launched. It's launched. I'm looking at a snapshot like midway through its flight time and then all the way to the top. So snapshot A is just after it's launched, snapshot B is somewhere higher up, and snapshot C is at the top. Again, it's all one motion, but just different moments in that motion. So to start off, to draw my energy diagram, I also call it an LOL diagram because you'll be laughing at how awesome it is, how great it is to use to solve energy problems, whatever. Number one, it's in the system. What's in the system? Good practice, just put everything in the system. So ball, earth. Just keeping in mind like gravity, the strength, the energy stored in gravitational potential energy, it's an interaction. You can't just have a ball and it having potential energy. You need it to be in a gravitational field. So that's why I want to put the ball and earth in the system. The next thing, where's energy stored in A? So I see that there's no springs involved. There's no heat loss. I'm ignoring the air resistance. So the only places where energy is stored, kinetic and potential here, kinetic and potential also. So this is snapshot B, this is snapshot C. I'm then going to basically just arbitrarily assign a certain number of boxes to the kinetic energy or the potential energy, depending on, if it has it at that moment. So snapshot A, I just want to recall the kinetic energy formula is 1/2 mv squared. So if there's mass and there's a speed, then this thing has kinetic energy. So at snapshot A, it is moving at 10 meters per second. It has kinetic energy. I'm going to just randomly draw 5 boxes. Just doesn't really matter how many boxes you draw. Doesn't matter the height. I just want to say it's sort of like accounting for there's energy and kinetic. Potential. Is there energy and potential? The equation for gravitational potential is mgh. And if my height is 0, which it is in snapshot A, then there is no potential energy. All right, what about snapshot B? So it has a speed of 5 meters per second, so it's less. And then potential energy, it is now at some height, so there's some potential energy. And now here's the little subtle part. The whole thing with energy is if there's no energy entering or leaving my system, then the total energy here, let's say if I have 5 boxes, should be equal to the total energy here. So that's where the boxes come into play. I should be showing kinetic conservation of energy with these boxes. So that's why. Just make sure the boxes match. Now, I could have boxes entering or leaving the system, in which case, boxes here plus boxes entering is equal to this. Like that would be an equation. And I hope you see now this lends itself to an equation. So you want to translate this into an equation. Basically say the energy here, in this case, it's like just the kinetic energy. This is A. So in Regents, you're never going to need to keep track of usually more than one snapshot. It's very rare. The problems are usually just A and B. So initial and final will probably be okay. But here, since I'm using snapshot A and B, I'll say kinetic energy at A. There is no potential energy. So that's going to be equal to the kinetic energy at B plus the potential energy at B. And that's my general equation. Now, if I substitute in the variables, 1/2 mva squared is equal to 1/2 mvb squared plus mghb. And now the final step is really just substituting in what I know and solving for what I don't. So in this case, I was given the speed at A, the speed at B, but I don't know the height at B. I don't know the mass, but in this case, the mass actually just drops out. I know what the gravitational field strength is, so I can just solve this. I didn't even want to do the actual numerical part, the key here is the concept. So I want to just review. What's in the system? Ball on the earth. Where's the energy stored? It was moving, so it had kinetic energy. It was at height 0, so no potential energy. Then I look at B, like did the kinetic energy increase or decrease? That's kind of helpful. And it slowed down. So that's why the kinetic energy went down. Potential energy, did that increase or decrease? Well, the height went up. Mass and gravitational field strength stayed the same, so potential energy increased. And now I just got to make sure that the total number in the beginning is equal to the total number at the end. I didn't lose boxes. So that's what that equals sign is telling us. And that's basically how you use energy diagrams. We'll do practice tomorrow in class. See you then.